All right, friends and neighbors, welcome back to another networking video. We are going to start a series on network address translation, or NAT, and this is part 1. We're going to do an introduction and we'll do a demo with this one. And before we dive in too far, network address translation is something that almost everybody uses every single day. It requires a translator, that's usually a router or a wireless home gateway, which is why I say everybody uses it. If you've got a NAT box or a wireless home gateway on the edge of your network, you are doing wireless or wired network address translation through your router. And so it doesn't matter if you got a Linksys or a Dinglink or a Belkin or anybody else, you are probably going to be doing network address translation. And this is especially true if you've ever looked at your IP address and you have a 192.168 something IP address. Now these are all pictures of wireless home gateways, no antennas, 2 antennas, 3 antennas, 4 antennas. It doesn't really matter because we're not really interested in the wireless stuff at this point, because it eventually all goes out through your internet port or your iNet port or your WAN connection. And so for that reason, we're not really worried about what's going on wirelessly or wired for that matter. What we really care about is what's going on inside the box from one side of the router to the other, and that is network address translation. So here's our basic problem, kid. From RFC 1631, that's sort of the early one, dates all the way back to 1994. And like so many of the issues that we talk about, when we talk about masking, subnets, supernets, aggregation, routing table sizes, it all comes down to the growth of the internet. And so, even back in 1994, which if we sort of put this in context, it was just 10 years after the very first sets of RFCs started coming out. Most of the protocols that we use date from the mid-1980s. 10 years later, this is catching on like wildfire, right? The first graphical browser comes along in 1994, Netscape, and we can see everybody's coming to the party, as Jeff Goldblum would say. So, the two most compelling problems facing the IPv4 based internet are IP address depletion, that means we're running out, and we're already out and have been out for years, and scaling in routing, right? Routing table growth. So these are the two biggest problems, and at the time, both long-term and short-term solutions were being developed. The short-term solution was that we were going to do classless interdomain routing. We were going to get away from straight-up class A, B, and C, and we were going to go to being able to do anything we want with the mask. So we could subnet, we could supernet, we can aggregate routes, we can do route summarization, and that makes our routing table size collapse. The longer term solution was to develop new internet protocols with larger addresses. IPv6, okay? But in the middle of all this, while we're waiting, here's a network address translator that you can work with, and that might help. Now it turns out that the world absolutely loves network address translation, but why? Well, when we start to take a look at IPv6, its use is growing. I mean, there used to be a World IPv6 Day. You can actually go out and look on the web on that stuff. But IPv6 is a bit of a pain. It doesn't operate exactly like IPv4. There are a lot of similarities, but we start off with those enormous addresses. And then we say things like there's no broadcasting. And then we say we're going to make use of lots of multicast stuff. And all of a sudden IPv6 starts to look a little bit different. We've got to change DNS entries, all of that. So a lot of people said not want IPv6. So the deployment of IPv6 didn't exactly go as planned. It also turns out that network address translation, or the translators, worked really, really well. So it almost didn't matter that we ran out of IP address space. I mean, it does, but most people don't know that. Even if you're on a NAT network, you don't really know that because everything works, and everything works really, really well. There were some hiccups early on, but today it works really, really well. So from RFC 3022, that's the the RFC that came after 1631, it actually deprecated 1631. We have the traditional IP network address translator. And traditional is a keyword and tricky phrase here. The need for IP address translation arises when a network's internal IP addresses cannot be used outside of the network, either for privacy reasons or because they're invalid for use on the outside network. And this is our first indication that we're really talking about private and public address space. So wait a minute. Invalid IP addresses. So again, this is the discussion between public and private. Now, invalid in this case means that you can't use it on the public internet. And so there are a collection of addresses that we call private addresses that we don't use on the public internet. They can be routed, so internally you can build routers that route them. You can build a whole massive infrastructure just using private addresses. But they're no good on the public internet. No public router will route them. In addition, there is a tie to public resources. So we don't use any public resources that can be resolved to a private address. In other words, public DNS or public name servers do not have any private addressing in their resource records. So we don't do that on public DNS. You can do it on private though. You can absolutely build your enterprise scale network and internally have all private addresses and have private DNS that use private addresses in their resource records, but it doesn't work on the public internet. So to go along with this whole idea of a translator then, we need something that handles our private addressing. And this is why we have RFC 1918 private addresses, or the address allocation for private internets. And we can see that if we go to RFC 1631 1994, the private address is 1996, and then the update to 1631 2001. So this is all happening, right? 1995, 1994 to 2001. Okay, so RFC 1918, this document describes address allocation for private internets. This allocation, or the allocation, permits full network layer connectivity among hosts inside an enterprise, so it doesn't matter how many you have, and then you can, all of those private hosts can still get out to public hosts, and then vice versa. So we'll have to talk about how that works here in a second. So before we get to our demo, let's talk a little bit more about RFC 1918. So this is a busy slide, there's a lot going on here, but let's just unpack it a little bit. Okay, so it's been typical to assign globally unique addresses to all hosts that use TCP/IP. Okay, so what that means is that historically what we would do is you would build a network, and every single one of your hosts would have a publicly valid IP address, meaning that everybody on the public internet could see that node and its IP address. Now, it's quite likely that when the organization would connect to the internet to achieve internet-wide IP connectivity, which is what we all want, the organization would need to change IP address, renumber all of its public hosts, regardless of whether the addresses used by the organization were initially globally unique or not. So that means that when we're switching to private addresses, you would have to renumber or change the IP addresses of a whole bunch of your hosts, even if they had public addresses before and still needed to get to the internet. So, an enterprise that decides to use IP addresses out of this particular address space can do so without any coordination from IANA or an internet registry. All right, remember that we have the regional internet registries. So, if you are using RFC 1918 addresses, you don't have to ask anybody's permission. Everybody can use the same address space. It can be reused over and over again, and you don't have to talk to anybody. Where previously, if you were using public addresses, you had to get permission. You had to get a release from your ISP or an RIR or even IANA. Okay? So the address space can be reused between multiple enterprises. The only place now that a node has to have actually a unique address is now just within your enterprise. You're just going to avoid reusing that same private IP address somewhere else in your enterprise. Okay, So here's the thing that we all know, right? When we start talking about RFC 1918 addresses, we say we got one for the 10 net. That's a /8 prefix, right? 255.0.0.0. We have one for what looks like class B, 172.16, but it's 172.16 to 31. So that's actually a /12. So it looks like it's part of class B, but actually the space is not the same as a straight up class B address. It's actually much bigger than that. And then we have what looks like a class C network, but it's actually got a /16 prefix, and that means that it's actually a class B allocation in terms of size. Okay, now just one other note on the /12 prefix. I have it in red there. So the range of 16 to 31 looks like what I have there, you know, this part right here. This is 16 to 31. And the reason that all of these match this mask is because the mask is a /12. So in the second octet, there are these 4 zeros. And anything ended with these zeros gives me a 0. So that's why the range in these 4 is 0 to 1111. Doesn't matter because when you do the ending, they're all the same. RFC 3022, the Traditional IP Network Address Translator. This is what your Linksys or your D-Link or whatever your home gateway or your wireless home gateway does. It does what we call Traditional NAT. And what this means is that every single address or every single transmission coming from the inside network, that is your private network, on its way out to the public internet appears to have been translated so that it looks like it comes from the outside interface of your router. Everybody on the public internet believes that the transmission came from your router. So even though you might say, okay, I sent this packet, when it gets to the NAT router, the router says, oh no, I'm sending this, and then it goes on the outside. Now, we do have to solve the problem of getting it back in. We'll talk about that here in a minute. The IP header is actually rewritten. It might have started off as the source being the private addresses, but when it goes out onto the public internet, the source is actually this public interface on the NAT router. So as I said, that's what happens on the outbound side. But what happens when it comes back? Right? You're talking to a web server or you're pinging something and you send traffic out. It gets translated so that it appears to have come from the router. But when it comes back, what happens? Well, it actually comes back to the router. And then the router says, oh yeah, this conversation, that's right. I remapped this and I kept a table. And so if I'm an inside node, maybe 192.168, right, something, and I'm talking to this address on the outside, which is public, what happens is the router remaps to its public address on the outside and then sends it on. And when it comes back, the transmission comes back to your router, and your router says, oh, I am going to remap that IP address and port combination back to the host that I changed it from before. So I'm going to change it back to this. And so that's what the translation table is all about. Keeping track of all the things that the router modified on the way out so that we can remap them on the way back in. Well, let's do a demo. So here is our basic router topology, right? And so we're going to set up network address translation on our NAT router here in the middle. So just as a little bit of level setting, right? Here is our configuration. This host is 192.168.1.1. And so maybe what we'll do is we'll add some labeling here. Okay. And the default gateway for that host is going to be 192.168.1.254. And this host way over here, I'm pretending to be Google, and that'll be 8.8.8.8. And then the other side of this router is going to be 8.8.8.254, like that. Okay. So what we want to do, we want to be able to ping from here to here. Now, if I didn't set up network address translation, it would just be straight up routing. But what I'm going to do is I'm going to say, we'll go to int of 0/0, and I'm going to do a couple things. Oops. I'm going to go, first I'm going to say, here's your IP address. IP address is 192.168.1.254 and 255.255.255.0. Okay. Now what I'm also going to do while I'm here is I'm going to tell the router, and this is sort of Cisco speak, but every vendor has a similar thing. I'm going to tell the router that you have an inside or private network. So I'm going to say IP NAT inside. And that tells the router that it is the inside address for NAT. So I might say something like this. Over here I said IP NAT inside. Okay, so this is the same as the private address space. This is why I put AKA inside up here. Okay. Well, let's go over to F0/1, and I'm going to say IP address, and I'm going to say 8.8.8.254, but the mask will be different because it's a class A on the outside. And I'm going to say IP NAT outside. Now, just as an aside here, we're doing a straight up IP NATing from a private address space to a public. But translation doesn't really have anything to do specifically with private networking. So you can actually do translation all over the place, whatever your address space is, and you can have a NAT box behind a NAT box behind a NAT box. So you can do all kinds of translation. We're doing a very straightforward example here. So that means what we've done here is I said IP NAT outside. Spelling counts. There we go. So that's our base configuration. Now I haven't told the router how to do network address translation right now. So maybe what I'll do is we can say translation configs. And there's a couple of them that we can use. We could say I'm going to use a pool of addresses. I could use a static addressing, static mapping, an address from the inside to the outside. Or I could do something called overloading, and I can use access lists. There's all kinds of things that I can do to set up my translation. Since we're talking about something that's very, very traditional, I'm just going to do a translation from this node to the outside. And maybe I'll do it two ways here, and I'll show you the behavior of the router. Now, one important point to make is that while this router has an IP address, it's not necessarily the case that the translation occurs on this particular IP address. It could be another IP address that's valid on this network. And so that's the way that I'll do this first. What I'm going to do is I'm going to say IP NAT inside. So I'm saying specifically I want to translate somebody that's inside to this address on the outside. So inside source, and this will be a static mapping. So I'm going to say 192.168.1.1 will be remapped to 8.8.8.99. Okay? So what this is saying is that whenever you see traffic from 192.168.1.1, translate it to 192.168.8.8.99. So there we go. Now for this, what I'm going to do is we're going to turn on our simulation here. And I'm just going to ping. So here we go. You can see that I did some testing either. So I'm going to ping. We'll let this go. So there's the ARP traffic to and from my router. And here goes, oh, let's do one other thing too. We're going to edit filters here. We're going to get rid of some stuff we don't want to see. We don't want to see CDP, TTP, STP. Oh, that should do it. Yeah. So we're going to step through this. All right, so the first one bombs out because of the ARP tables being updated. Here goes the ICMP. And there it is on the outside. Okay, so what does this look like on the outside? Well, let's actually see what it looks like on the inside. So from PC0 to the router, we can see that this is coming from 192.168.1.1 and it's going to 8.8.8.8. All right. But on the outside, what does it look like? Ah, it's coming from 8.8.8.99 to 8.8.8.8. So what happened here is that the internal address of 192.168.1.1 got replaced by this address right here, which is what I specified in my static NAT command. And we can see that now this works. Okay? And if we take a look at, let's go back to real time here. If we take a look at the output, it looks like it's working just fine. Now, how did the router keep track of the outbound connections and how they come back in? And that was what I showed you previously. So if we do a show IP NAT translations, there they all are. So this is what I'm using on the outside interface. And this is what I was using for the private address. And here are the destinations, right? So the destination didn't change for either one of them. What I was changing was the source IP address. And this is the table that I use to keep track of that. Well, now let's do one more thing here. Let's change that. So I may have thrown you a curveball by using an IP address that doesn't actually exist on the network. So what I'm going to do is get rid of this. I'm going to say no to that. And I'm going to change it to 254, just like that. Okay? So now if I try it again, here we go, we're stepping through. ARP tables are already populated, so we don't need to ARP anymore. And that looks pretty good. But what does it look like on the outbound side? Did we change anything there? No, we didn't. There it is. It's still 192.168.1.1 to 8.8.8.8. But what is it on the outside now? Hopefully I did this right, so I don't have egg on my face. And there is the translation to the IP address that I just specified, right? 8.8.8.254 to 8.8.8.8. So if we go back to real time, we'll make sure it finishes. There it goes. Now if we go back to our router, and now we take a look at our translation table. Here we have the new mappings. So it doesn't matter how many times that we do this. You can see that we've got an increment number here. This one happens to be for an ID in the ICMP header, but otherwise it would be a port number. But that's how we keep all of these separate. It doesn't matter how many transmissions you have going out. They get remapped to different values, and then we have a way to keep them separate, even if we have a whole bunch of them. So hopefully this helps you with the basic operation of the IP Address Network Translator. All right, so what we've been talking about today is the Traditional Network Address Translator. So again, what happens when you translate? We're changing the IP addresses and specifically the source IP addresses. When we do that, we also have to recalculate the header checksum. And that's actually what takes the lion's share of the time to do translation. Translation actually is a heavy load on the router. Imagine that you have to translate every single IP packet, and there are millions of them per second. So it takes a lot of work, a lot of time just to rewrite the header, but also we have to recalculate the header checksum because the IP address just changed. We need to keep track of the table because we're going to remap the address to the original source address when it comes back in. So what we're really talking about is we go from private to public, and then we go from public back to private. Whew. That was a lot for our traditional network address translator. Thanks very much for watching. Thanks for listening. Hey, like and subscribe if I helped with your NAT understanding. And whether you're being translated or just routed, may those packets always reach their destinations.